Hey, everybody. So this is a super interesting research paper that caught my attention called Capturing AI's Attention, Physics of Repetition, Hallucination, Bias, and Beyond. In this particular research paper, they make a lot of claims within this paper, and then they go through a lot of analysis with regards towards physics, specifically the attention mechanism, transformers, and AI. And the bottom line within this paper, it's something that I've said a lot within this, right? Which is that it doesn't matter whatsoever, essentially, that if you know the theory behind an actual situation in a real world situation. Meaning that I think academia always often has this kind of backwards stance where you do something and then it's like, well, it works in practice, but how or does it work in theory? And then the question of does it work in theory becomes like this driving question, as opposed to what the question should be is how does it work in theory? So it works in practice. How exactly is this working? And then I think that it's important to take that extra additional step. And I don't see a lot of papers that are taking that additional step, right? And then so this is one of them. And this is put out by the physics department of George Washington University. And then in this, essentially, they break down how they try to explain how LLM models work through a complete physics approach. And they break it down very specifically to the attention mechanism in and of itself. And then so going back to that equation of it works in practice, but how does it work in theory? To me, we keep coming back to a lot of things about the transformer mechanism in and of itself. I think to me, a bottom line within this is I kind of, as a researcher within this, my bottom line hypothesis, one of my hypotheses within this is that we kind of just stumbled upon a lot of accidental advantages with the transformer architecture in and of itself, right? The transformer architecture, and this paper talks about this pretty significantly. So, AI models weren't built and transformers, the sigmoid function, etc., weren't built with physics in mind, right? They were built for computer science and around computer science. And then so often there's kind of a little bit of a disconnect between physics and computer science in this aspect. And then so physicists are often hesitant to explore the AI space because it's more of a computer science type of space. But within this, what we have is a computer science approach that has a lot of physics characteristics, and we can't explain 100% at the moment the full physics behind the actual architecture and how it's working and what exactly is going on within that. And then so that's essentially creating a physics problem overall, and then also additional avenues and explorations within physics. And then it's to me you're seeing a lot more and more kind of a connection between AI and physics in this way. But so within this particular research paper, they break down and they look at the n-body problem, and then specifically the two-body problem versus the three-body problem. And then what they come to the conclusion of is that if you look at the architecture of transformers, exactly how it works, this diagram that we're looking at here, right? So the update prompt to k equals 3 tokens, etc. What they're showing here and what they're demonstrating here is that this is the functional equivalent of a two-body problem within physics. And then it kind of just, again, accidentally just stumbled upon that the full transformer unit in and of itself, and how this architecture works. We know it works like a kind of like a credit card system at this point, right? And that wasn't known in 2017, but so that's how this architecture as a whole works. It's kind of like a credit card that you can charge compute to. And then how you're able to do that and why you're able to do that from a physics perspective, these researchers at least are proposing, is that it can be boiled down to a two-body problem. And then and so that the attention mechanism essentially operates like a two-body equation. And then so what is the n-body problem overall, if you're not familiar with it? The n-body problem in physics is very straightforward. It's with regards towards how entities celestial bodies orbit around each other other when there's multiple bodies, right? Celestial bodies is like the classical definition of the n-body problem. So, and like this diagram that we're looking at here, you've got 1, 2, 3, 4 bodies, right? It's 4 celestial bodies, and then how they're, or 5, yeah, 4 celestial bodies that are orbiting around the sun, right? And then how exactly does that operate and function within that? And then very specifically, you have the 2-body problem and the 3-body problem. The 2-body problem is how 2 bodies go orbit each other. And there's very simplistic and normalized ways in which 2 bodies can orbit each other, right? They're generally like circular paths, and then elliptical paths, Euclidean paths. Whereas with 3-body problems, generally you need to like bring in a lot more calculus into it, and then you can also get into kind of weird shapes and weird dynamics, like we're looking at here, like right? Like you can solve the 3-body problem via like transposing triangles on a sphere, for example, is one solution to the 3-body problem, like this, right? And then so there's different ways and different ways to, and functions and avenues to go about this. But the bottom line is that there are problems that you can solve and advantages to a 3-body problem versus just a 2-body problem. And then so they outline that very specifically within this paper. And then so what their end argument is that the way that the n-body problem functions is in alignment with the transformer architecture overall, that the transformer architecture essentially formulates within the attention mechanism very specifically a 2-body problem, and then their analysis is that if we created that and made it a 3-body problem as opposed to a 2-body problem, that the models would actually function better, and that we would be able to fully explain how the models work via physics overall. At the end, the only thing that they give is really this kind of like mathematical equation and this mathematical breakdown as to how they think it would work with regards towards a 3-body problem attention head mechanism. And then so I take that, and then so I want to take it a step further, right? What would that actually look like in code? So explaining out what is going on here. So the connection from the classical n-body problem. So again, like the n-body problem is like planets orbiting a star, right? So we're taking that and then we're going to the attention mechanism in AI. So notice that overall is an analogy based on mathematical structure. And so here's how they're building that bridge, how we get from celestial bodies and orbiting celestial bodies to the attention mechanism within AI, right? Seems like kind of like a crazy broad connection. So first is that tokens are operating as bodies or spins within the AI model. So in the AI model, words or parts of words or tokens are represented as high dimensional vectors or embeddings. The paper conceptually treats these token embeddings as analogous to physical entities like spins in a physical system, or more loosely, like bodies in the n-body problem. These aren't physical objects, but abstract mathematical ones. So each token is is part of the 2-body problem. Attention mechanism as interaction. In the classical n-body problem, the bodies interact through physical forces, primarily gravity. In the AI attention mechanism, the interaction between tokens happens through a series of mathematical operations involving projections, query, key, value matrices derived from the token embeddings and learned weight and matrices. The core calculation, attention score equals query times key to the power of t, determines how much influence tokens have on each other. Mathematical equivalence, 2-body. The key step in the paper is demonstrating that the core attention score calculation, q times k to the power of t, is mathematically equivalent to a 2-body Hamiltonian from physics, and then the full Hamiltonian equation. So this is the attention mechanism, right? This is the common formula and the equation for the attention mechanism. And then what they're doing, these physicists are just pointing out and saying, hey, computer scientists, this particular equation is actually mathematically equivalent to this equation, and this equation happens to be a 2-body Hamiltonian from physics. Overall, there has to be a physics way that these models are working overall, right? So they're making this correlation. A Hamiltonian in physics describes the total energy and interaction within a system. Here, the weights, or the embeddings, SI and SJ, are 2 token embeddings, the 2 bodies or spins, and then I and J, right? They represent the 2 bodies in our equation. W efficiency derived from the learned Q and K weight matrices. So the weight whole weight mechanics acts like the interaction between potential or force field mediating the interaction between the two tokens. Therefore, standard attention is interpreted as modeling primarily pairwise two-body interactions between tokens. They're just essentially modeling this out as a physics problem, as a two-body problem, extending the analogy so how they get and why they think a three-body problem would be better. Just as the classical two-body problem, like sun and earth, is solvable and predictable, while the three-body problem, like sun, earth, and moon, becomes vastly more complex and often chaotic, the paper uses the difference as an analogy. The success of current LLMs suggests that these two-body interactions captured by standard attention are very important for modeling language. And then this is an important claim that they make within this research paper, right? They're essentially saying that the way that the models solve for language in this instance is that language can be broken down into a two-body problem, and then essentially the two-body problem would be getting from the abstraction, like one abstraction, to the more pure, the more platonic abstraction would be the best way to do it, right? The best way to represent it, and these would be rather than celestial bodies, they'd be logical entities, logical bodies, right? But it's still like we're dealing with abstractions, geometry, shapes, like all of these same concepts that I talk about, I've been trying to talk about and illustrate a lot. We have just, more and more coming together of this and these concepts from a physics perspective, and more people understanding that this problem has to be tackled from a physics perspective. So I think all of this is great overall, right? So the paper speculates that to capture even deeper, more complex relationships in language and reasoning, analogous to the complexity introduced by a third body in physics, the attention mechanism might need to be generalized to explicitly model three-body interactions or even higher order n-body interactions involving triplets or larger groups of tokens simultaneously. So essentially, if the current token mechanism is token 1 and token 2, and they operate as kind of like celestial bodies orbiting each other, let's make it token 3, token 4, and then so you kind of have 4 tokens in there orbiting each other, and then that creates a more robust, more chaotic, but also a more robust system. So in essence, the jump is made by treating abstract token vectors as analogous to physical bodies or spins, mapping the mathematical operations of attention onto the concept of physical interactions, showing a formal mathematical equivalence between the standard attention score calculation and a two-body interaction Hamiltonian, using the known increase in complexity from two-body to three-body systems in physics to hypothesize that a similar three-body attention could unlock more complex capabilities in AI. Remember, it's an abstraction that leverages the language and mathematical framework of physics to understand and potentially improve an AI mechanism. So what exactly and how exactly would this three-body attention mechanism work? Here's the full code for you, like lots of like notes and details within this, right? Again, they don't give any sort of framework for this code framework in this particular formula here. I do have, and I can conceptually state that I think so there's other papers that I've seen that have approached this problem very specifically within this. There's another algorithm that I've mentioned quite significantly on this channel at this point called torque clustering, right? I've actually made a video on torque clustering, and someone on that video, they asked a question, they asked if my version of the torque clustering that I laid out utilized essentially parameters, whereas the original torque clustering didn't, and they asked if that kind of difference made any sort of difference. Generally speaking, I'm kind of, my approach is more hands-off with regards towards communication overall at this point. Just my kind of bottom line approach, right? I've kind of separated my full income completely from having to communicate at all, and so my income and having to communicate with people are very divorced at this point. And then I'm just kind of introvert anyway, and then so if you divorce economic incentives, I'm just you could extrapolate that to whatever you want. There's no reason to participate within the system if you divorce the economic incentive from it, right? And then I think there's a lot of lessons that can be learned in the broader world within that context, but I'll leave that there. But so diving into what we're looking at here within the code, a conceptual example of a three-body attention mechanism. And then remember, this is a simplified illustration inspired by the paper suggestion, not a standard or formally defined mechanism. It calculates scores based on three projections. So in this instance, I'm using Q, K1, and K2 instead of the standard two Q and K. So I'm splitting K into K1 and K2. As I was mentioning before, there is an algorithm in a way that I think would be better than this system, which would be torque clustering and the torque clustering algorithm overall. I think that the torque clustering algorithm would be better than what I'm laying out here. The author has licensing around the torque clustering algorithm itself, so I try to be respectful of that, right? In this is just my own interpretation, like very different from the torque clustering algorithm overall. I'm taking this based off of their three-body attention, their three-body problem, and the three-body attention head, and then creating essentially a three-body attention head where I'm splitting the standard Q and K into Q, K1, and K2 to give it three attention. And we could split that further, right? So my goal with that would be that if you wanted a four-body problem, you could go Q, K1, K2, K3, K4, etc., right? And then so from there, you need to make sure that your embedding dimension is divisible by number of heads. So you need to do, if you do Q, K1, K2, K3, you need to update the math overall, is the bottom line, right? And then I just lay out the three-body part, how exactly that looks. All of the code here, I ran it through multiple times to give it it's if you want to run through this and they don't give you anything as far as the code in that paper, right? So here's everything that you would need to construct a three-body attention head overall. I'm just trying to make it as notation heavy as I possibly can, because it's not actually hard. Their concept, what they laid out, and they laid out all of the math, right? And so that was part of the good thing. So I didn't have to do a lot of the math, but it's sometimes hard to take math and then put it into code, which is what I've become very good at doing this for 3 years now. And then so within that, that's kind of what we have over here. So here's the full explanation and the full breakdown of what we're doing here, right? So first of all, we're creating our attention head with our parameters. So Q, V, K1, and K2 projections from the input of X, which is typically, that's a very standard process except for the K1 and K2, right? Then we're reshaping. We prepare these for the multi-head processing, which is standard and typical. Then we do a score calculation, and then so the core conceptual change is here. So our score base are calculated like our standard attention utilizing Q and K1, but then our score modulate calculates using Q and K2, represents the influence of the third body interaction, and then we have a modulation factor, which is an activation function, is applied to these scores modulate, and then we have the combined scores, which is the base score is element-wise multiplied by the modulation factor, and this conceptually means that the attention score between the token J, represented by QJ, and token I, represented by K1 and I, is modulated based on how QJ interacts with all K tokens. Then we have the softmax. So we apply to the softmax of the combined scores to get the attention weights. Then we have the weighted sum, our standard calculation utilizing the attention weights of V and NV. And then finally, we have our output projection final linear layer. So 4, 5, and 6, we go back to standardization. It's 3 is where most of this mathematical complexity is being added, right? 1 and 3 are where we're changing the equation, the standard equation. And then we get our standard result, right? This is just the standard shape, input and output shape of the neural network head and of the attention mechanism, right? So we're just outputting that. And then so here it is, right? And then this is a 3-body attention head as opposed to your standard attention mechanism. And then so this is just really taking your standard attention mechanism and then making modifications here and then here. And then that's kind of overall what we're looking at within this. And then so this is the 3-body attention head as posed in the research paper here, capturing AI's attention, physics of repetition, hallucination, bias, and beyond. I'll leave a link to both this research paper as well as the Google Colab notebook. If you like this type of content, please like and subscribe. Thank you very much.